Okay, so thanks to Joao, he introduced many concepts I will use in my presentation. So this is a work of a logician on explainable AI. So I'm looking at this problem from the point of view of logic, from non-classical logic. So I will spend a few words on what is non-classical logic. So let me start with this nice quotation from Spinoza. He's one of the most important philosopher in modern philosophy, which is basically saying here that every phenomenon can find an explanation for it. So it's called the principle of sufficient reason. So we have to take explanation seriously based on this idea that most of AI system can be explained in principle. So we look at the explanation from the point of view of logic. So the first statement, which is important, is that most logic-based approach to XI use propositional logic. So that's something we saw in, for instance, the presentation of Joao, is mostly based on PL. So now the point is why we should go beyond propositional logic. Well, because we want to build more expressive languages for instance, capturing counterfactual reasoning. Many people nowadays, they talk about counterfactual explanation. So when you, for instance, Nicola, so what is the basis of counterfactual explanation? Is the idea that you have this kind of reasoning which imagine alternative possibilities. So you are reasoning in a space set, so you have a set of possible worlds, and you have to reason about these alternative possibilities. Then you also want to model black box classifiers, for instance. So behind this idea of black box, there is the idea that I don't fully know the classifier, right? So the function is not fully known, so there is some level of uncertainty or partial knowledge of the classifier. So if you want to model that in a logical way, you need to model uncertainty, okay? And then finally, this is more in line with game theory. Many people nowadays, they want to model interactive explanation. Namely, you have a multi-agent system, many agents, and they provide explanation to each other in a dialogue game. So to model that, you need logic plus game theory. So that's the reason why we need to go beyond the propositional logic, and non-classical logic is just the family of logic which are more expressive than PL. So I'm just listing here a few of them: modal logic, conditional logic, epistemic logic, and game logic. And these are the basic tools that we have been used in the last couple of years to model this kind of notion, since we think that you need expressive languages to model explanations. Okay, so this is a classifier, it's a function. So this is these are the table of a classifier. So it is in line with what Joao presented. Well, everyone used this example of the loan. So you have instances. Each instance is defined by a set of features. So you ask for a loan, and the bank will accept your request or not, depending on your features. So this kind of is monotonic, this classifier, right? So there are three features. It's a very simple example. You can have a permanent job, you can have a high salary, and you can be European or not. And that, depending on these features, the bank will decide whether to accept your request or not, okay? So this classifier is a white box. In which sense? The function is known. I mean, you have the table which fully represents the function. But the claim here is it realistic, this situation? Do we always know the function? Well, not always. Most of the time, the function is not known. I mean, it's rare to have this kind of table. Okay, so now the first logic we developed is a logic for white box classifiers. So, and to model this kind of classifiers, you need to take from the shelf probably the simplest non-classical logic, which is the modal logic S5. It's a very simple logic. So, well, I just give you the idea how you work with S5. So you can see a classifier as a set of states, okay? Each instance is a state, okay? Look, I mean, you can see state as a synonym of instance. And then beside the state, the instance, you have the classification function. So this is a model of S5, right? So it gives you a partition of the set of possible states depending on the classification. And on the top of that, you can construct a very simple language. That's the first language we built. And this kind of modality, right? Just to briefly explain what does it means. So basically, this formula, which is a formula of this logic S5, says that if you have a permanent job, necessarily you will get your request accepted. Okay, so PEI is an implicant of getting the request accepted, okay? So now, in this very simple language, we were able to provide a big taxonomy. So we took most of the definition from the XI literature. We were able to translate, to encode them in this very simple language. And then we came up with a comparison and with some complexity results. So I'm just listing here some of the definition we were able to write down in this simple setting. So we model prime implicants. We model abductive explanation, so I don't need to explain what an abductive explanation is since Joao already explained. We have contrastive explanation, and nicely we can model counterfactuals. So since we are this kind of modal logic and Lewis theory of conditional, which is probably the most famous theory, logical theory of conditionals in modern philosophy, is based on this kind of models. Okay, so you use this kind of Hamming distance. You have a distance measure between states, and yet you can represent counterfactuals. And we prove properties. For instance, this is the translation of Spinoza principle. You remember Spinoza principle is saying everything can be explained. We prove that. So if you have a white box classifier, there is always an explanation of it, at least an abductive explanation. And then we were able to, because there is also some confusion in the XI domain. Someone talks about contrastive explanation, other people talks about counterfactual explanation. So the question is, what is the connection between the two? So what we were able to prove is that when the explanans, the explanation is atomic, is a literal, then they coincide. So contrastive and counterfactual are exactly the same thing. Now, when you have explanans which are terms, conjunction of literals, this equivalence does not work anymore, so they differ. But in the atomic case, they are exactly the same thing. So then, once you have the model and you have the language, you can reason, can do reasoning over that and automate the reasoning. So you can compute abductive explanation, contrastive explanation, and so on and so forth. So you can reason on the top of a classifier with this kind of formal language. Now the point is, what is a black box classifier? Now things start to become more difficult and you need more expressive languages. So again, so what is a black box from the point of view of logic? So you have to buy this idea. Probably you will not buy it, but that's what the stance we took. We say a black box is just a classifier of which I have a partial knowledge. I have imperfect knowledge of the function. So once you get this uncertainty level, automatically open the box of epistemic logic. So you have an agent which does not fully know the function. So he has a set of possible functions in his head, right? So you have a set of functions, right? And from a mathematical point of view, you move into the area of product logic. So you have a bidimensional semantics. Why this bidimensional? Because you have a vertical dimension, which is the dimension of the function. So you move along the classifier. And then you have an horizontal dimension, which is the dimension of all possible functions that the agent thinks possible, okay? And then I will give you complexity results. To reason that is very complex, is exponential. So this is the reason why black box classifiers are intrinsically complex. So let me give you an example what is a black box classifier. So here is the idea that when I start to look with a classifier, I don't know the full specification of it. I only have partial information. So suppose Bob is the agent who is reasoning with this classifier. He only knows three things. He knows that his application was unsuccessful. So Bob has a good salary, has no permanent job, is not European. Okay, so he's an instance of is S3. So he knows that his application was unsuccessful. He knows that if someone has a permanent job, he will get the application accepted. And finally, no permanent job and no good salary is a guarantee of unsuccess. Okay? So these three information generates a space of possible classifiers. So you can check, on paper. So these are the only two classifiers which are compatible with this with the three pieces of information, okay? And then you can represent these kind of situations in a B-modal language. So look, I was referring to two dimensions, And here, the 2 dimensions are given in the language itself. So we have 2 modalities, so there are 2 quantifications over the 2 dimensions, okay? So going back to Spinoza, now if you are in the black box, there is no guarantee of success. So that's what this theorem says. So if you are in an uncertainty setting like that, you cannot always find an explanation. Why? Because, well, you can check mathematically because abductive explanation requires minimality. So once you have many possible functions, minimality can fail. And that's the reason why in a black box setting, there is no guarantee of the existence of an explanation. Okay, now we were also able to model learning dynamics. So look, on the top we have Bob with this uncertainty. He does not know the function. So we introduce some extension of this logical language to reason about learning dynamics. So what we can model here, suppose Bob has this uncertainty. Now he gets this information. There is a bias in favor of EU citizen, okay? So it means that you can find 2 individuals, two applicants, which are exactly the same, except they differ on being a UI citizen or not. And then the first one will get the application accepted, while the second one will get the application rejected. So by getting this information, Bob goes into the second state in which there is no uncertainty anymore. So we have a language to reason about these kind of situations. And this is very important, for instance, if you want to model interactive explanation. Agents, artificial agents, providing explanations one to each other. Okay, so we have a complexity analysis of these different languages. So you can see, I think complexity analysis provide very interesting insights. So if you want to reason about what white box classifiers, you can use a SAT solver very easily. So if the function is is fully known, you can do abductive reasoning, contrastive reasoning, counterfactual reasoning, whatever you do it, and that's exactly what Joao was showing, okay? So reasoning here, I mean satisfiability checking, okay? I want to check whether there exists a model of my logic which satisfies a formula. That's what I mean with reasoning. Now, if you move from white box to black boxes, it's a disaster. You get a problem which is intrinsically exponential. Why? Because you can imagine, remember this situation of the 2 dimensions. So you have a lot of functions in the picture, right? So this makes the problem very hard. And we were also able to prove that we can model learning dynamics in a decidable way by this kind of dynamic extension. Okay, so there's the message here, black boxes are exponential. So, and now we are actually working on, that's kind of, the story goes like that, white box, black boxes. And this last step on which we are working now is interactive explanation. So you don't have a single agent in the system, you have a multi-agent systems reasoning about a classifier. I have my uncertainty about the classifier, you have your uncertainty about the classifier, and we are trying to give explanation to each other, and we are in this kind of interactive setting. And the kind of semantics is, so you need to increase more. So this kind of semantics are this kind of, you can use type structures, you can use multi-agent belief basis, and so on and so forth. But that's another story. And that's the publication this kind of the results we had in the last 2 years on these topics. Thank you.